Welcome to a new section. Today we are going to study electric field lines. We can represent electric field graphically by drawing curves known as electric field lines. It is invented by Faraday, who called them as lines of force. So another name of electric field lines as lines of electric force. These lines are just geometrical or pictorial representation to visualize the nature of electric field in a region. It also gives us the direction of resultant electric field at that point. Now, what is an electric field line? Electric field line is a curve drawn in such a way that the tangent at each point is in the direction of the net electric field at that point. An arrow is drawn on the electric field line to show the direction of electric field at that point. So we can say the net electric field at this point is in this direction, at this point is in this direction, like that. So the tangent at each point gives the electric field at that point. So electric field line is a curve that drawn to show the tangent to it at each point is in the direction of the net field at that point. So we can draw electric field lines for any cases. Now we are going to draw electric field lines for a positive and negative point charges. So first we are going to draw electric field lines for a positive charge. Consider a positive charge Q is placed here. We know the electric field is radially outward for a positive point charge. So if I draw curves in such a way that the tangent to each point will show the electric field lines, then that lines will also be radially outward. So the electric field lines for a positive charge is like this. What about the electric field lines for a negative charge? We know the electric field is radially inward. So the electric field lines are also radially inward. We can draw the electric field lines for a negative point charge like this. So we got electric field lines for a positive point charge and for negative point charge. That is, the electric field lines for a positive charge is originating from the charge and are represented by straight lines. Similarly, the electric field line due to a negative point charge is represented by straight lines, but they are terminating at the charge. So this is a two-dimensional figure we drawn for electric field lines for point charges. But actually these electric field lines are a three-dimensional figure. That is, the electric field lines are there in all the directions. That is, they are space curves. So we need to draw electric field lines in all the directions isotropically. What do you mean by isotropically? It means that we should draw lines uniformly in all directions. Now, let us draw some more lines here to understand more about these electric field lines. Now consider two equal areas, one near to it and one far away from it. We can see the number of electric field lines passing through the area near to the charge is more than the number of electric field lines passing through the area far away from it. What it shows? It shows that the relative density of electric field lines near to the charge are more than far away from the charge. We know the intensity of electric field for a point charge is more near the charge and less away from the charge. That is, if we draw electric field lines isotropically, then if electric field lines are crowded, that is placed close to each other, then the field is strong, and if they are placed apart, then the field is weak. We can draw electric field lines for charge distribution containing more than one charge. In the first case, we are going to draw electric field lines that contains two charges. Here it is two positive equal charges. We know if we place two equal positive charges, that is same charges, it will repel. The electric field here will be in this direction and the electric field here will be in this direction. What about the electric field here? We know it will experience a repulsive force from this charge. So what will happen? The electric field will have a net effect like this. Here a net effect like this. Like that, I can draw electric field lines for this charge like this. So if I draw the electric field lines, the field lines will be in these directions. If I place a positive charge plus Q and a negative charge minus Q, we know electric field lines will originate from positive charge and ends in negative charge. So the electric field lines will be like this. And it will originate in this and it will ends like this. It will originate and ends like this. So we are getting electric field lines like this. What about the electric field lines here? It will go in this way. So the net field will be like this. Like that, we can draw electric field lines that contains more than one charge. Now we are going to study some properties of electric field lines. We already studied electric field lines start from positive charges and ends at negative charges. We already studied this in previous figure. It will start from positive and ends at negative. If there are only single charges, then we know it will start or ends at infinity. So, if it is a positive, it will end at infinity, and if it is a negative charge, it will start from infinity. So, that is the first property, that is, we start from positive charges and ends at negative charges. For single charge, start or ends at infinity. Second property is that in a charge free region, electric field lines can be taken to be continuous curves without breaks. So, if there are no charges in a region, the electric field lines are continuous without any breaks. That is the second property. Third property is that two electric field lines never cross each other. That is, two electric field lines never cross each other, like this. Why it is not happening? Because if I draw a tangent at this point, that is at the point where it crosses, I will get two tangents for two curves. One is in this way and the another is this way. So, it means that an electric field in this way and this way. Is it possible that net electric field at a point is in two directions? No, it is not possible. So, two electric field lines never cross each other. The fourth property is that do not form any closed loop. What it means? If there is a positive charge and a negative charge, we know the electric field lines start from positive and terminates at negative. It is not possible to start from negative and terminates at positive so that it completes a closed loop. So, electric field lines do not form any closed loop. It will start from positive and terminates at negative. Fifth property is that the tangent to an electric field line at any point gives the direction of electric field at that point. Net electric field. Based on this, we are drawing the electric field lines. So no need to explain much about this property. Sixth property is that they are perpendicular to the surface of a positively or negatively charged body. That is, if you are considering a charged body like this, then the electric field lines will be like this. If it is a negative charged body, then there also we are getting an electric field lines which are perpendicular to the surface. Seventh point that we already studied, relative density is small where the electric field is stronger and vice versa. What it means? We already studied it. The electric field intensity is more, or the electric field is stronger where the relative density is more. So here it is strong electric field and here it is weak electric field. That is, the electric field intensity is more where the relative density of electric field lines are more. Eighth property is that electric field lines contract lengthwise to show attraction between two unlike charges. Ninth property is that electric field lines exerts lateral, that is sideways pressure to show repulsion between two like charges. We are going to see it in the figure we already drawn. Look at this case, these are two like charges. They are repelling each other. That is, they are showing lateral pressure. So this lateral pressure in the electric field lines shows they are repelling. For unlike charges, you can see they will contract lengthwise, and this shows the attraction between two unlike charges. 10th point is that electric field lines do not pass through conductor. As a result, we can see the interior of the conductor is free from the influence of the electric field. We will study electric field inside a conductor in another video. The last property we are going to mention here is electric field lines can pass through an insulator. So in this video we studied about electric field lines. Thank you for watching this video. Keep learning. If you are not yet subscribed to our channel, please subscribe it. Also please like and share this video.